Bismillah ar-Rahman ar-Rahim. Last lecture, we started discussing the synchronous counters, and we have shown the implementation of 3-bit up counter as well as 3-bit down counter. Of course, when we tell you to implement a 4-bit, you should be able to generalize the idea and derive similar, the lowest 3-bit are going to be identical to what we have here, but the 4th bit is going to be somewhat similar, okay, in concept, okay. So you should be able to generalize and come up with that yourself. Okay, it's all based on the identifying the conditions at which we flip the bit, okay, or toggle the bit. Now, if you remember, let me go back to the problems with ripple counters, okay? So if you remember that in ripple counter, as you go away from the least significant bit, the delay of the the output of the flip-flop, okay, gets increases as we go away or further from the least significant bit. Okay, so here we said that if the delay of the flip-flop is delta, okay, and the delay of Q0 is going to be delta, the delay of Q1 is going to be 2 delta, Q2 is going to be 3 delta, and Q, for example, 64 is going to be 63 delta, okay, which is too much, okay. But in the beauty of synchronous design, synchronous counter, okay, is that all the flip-flops, all the outputs of the flip-flops will have the same delay, which is delta, okay? They're not going to be rippled, okay? They're not going to be rippled like the ripple counter, okay? So all the flip-flops driven by the same clock signals, so therefore their delays are going to be identical. So you can see here the delay of Q0 from clock to Q is the same as Q1 from clock to Q, okay? And here as well, from clock to Q is the same for Q1, Q2, and Q3, and for all the 4-bit here, okay? We're showing here the timing of a synchronous counter here, 4-bit synchronous counter. Is it counting up or down? Anyone can tell me whether it's counting up or down.
This one is counting up.
Why? This is, for example, so this is 1, and then 1. You see? Oh, this is counting
Nice.
up, okay? Because this is Q0 and Q3. At least this is LSB and MSB. All right. So this is an up counter. Excellent. Thank you, Faisal. Ali, is it? Ali, yes.
Faisal, yes, Faisal Ali.
Okay. I sometimes get the names right, and sometimes I don't get them. So forgive me, guys. Okay. Here the delay of Q0 equals the delay of Q1 equals the delay of Q2, delay of Q3, and they are all constant, which is basically the delay of the flip-flop. Okay. So this is an excellent feature of synchronous counters. Okay. Let's move on to another topic. So we would like to use the counters for the for deriving another frequency. Okay, so basically what we are trying to do is to divide our clock frequency. So let's suppose that the clock frequency is too fast for our purposes. Okay, so we can derive something like half of the clock frequency. of the clock frequency, or even 1/4 of the clock frequency, and so on and so forth. So we can always use a counter to get powers of 2 reduction of the frequency. Okay, so if you see here, what is the period? This is also a 4-bit counter now. Okay, and this is the clock. Okay, what is the period of the clock? The period of the clock can be from here, for example, to here, right? Here all the way to here, right? Yeah. Or I can also denote it, or I take it from just to match it with Q0. Okay, I want to match it with Q0. It's from here. I can say, let's just zoom in. It's from here. Okay, just so where is the next point that matches this point here? It's this one, right? Exactly this one. So this is one clock period of the clock. This is P clock. Okay? This is the clock period. Okay? What is the period of Q0? What is the period of Q0 in terms of P clock?
Half of P clock.
Is it half? So this is the period actually. Yeah?
Oh yes, double the clock.
Twice.
Yeah, so it's double. The period is double, so the frequency is halved, right?
Half. Yeah.
Yeah, so because the frequency is 1 over the period, okay? So this is basically 2 P clock. Okay? And then this one here, on the other hand, so we can basically take from here to here, for example. And if you measure it, it will be 4 P clock. So the more you go, you multiply by 2 each time. Okay, the period doubles each time. You go, you advance with the counter bits. The reason for that, if you remember, you go back to the truth table or to the state table. Okay, you see that Q0 is flipping every clock cycle, right? And then Q1 is flipping every 2 clock cycles. And Q2 is flipping every 4 clock cycles. And Q3 is flipping every 8 clock cycles. Do you see that? So it's a matter of powers of 2. As we move from here to here, we multiply the period by 2. Each time we move 1 bit ahead. Okay. So yeah. So this is 4 P clock, and this is what? This one here is 8 P clock, right? And the last one will be 16 P clock, right? So what are the frequencies? For Q0, it is, the frequency is F over 2, where F is the clock frequency, and Q1 is F over 4, or frequency has a frequency of F over 4, and Q2 has a frequency of F over 8, and Q3 has a frequency of F over 16. So what about Q sub I? What is the frequency of Q sub I? Anyone can tell me? Frequency of Q sub I is F over what?
2 to the I plus 1.
Excellent, to the I plus 1, yes. And this is actually mentioned in the notes here. So the maximum clock frequency is the system clock frequency, which is this one here. Okay, so we cannot exceed this. Okay, We cannot double the frequency. We can divide by some factor. Okay, we can divide the frequency by powers of 2 if we use an n-bit synchronous counter driven by the clock with a frequency f. Okay, so bit number 0, as we saw, has a frequency of f over 2, and bit number I has a frequency of f over 2 to the I plus 1. Now, if we want to divide the clock frequency by an arbitrary number that does not equal to powers of 2, then what do? We use modulo n counter. Okay, modulo n counter. Before I discuss the modulo n counter, I will give you a brief overview of how to implement what we call. We have seen how to implement. This is a simple D flip-flop, right? It's a 1-bit register with a reset. What do we call this reset? Is it synchronous or asynchronous?
Asynchronous.
Asynchronous. So it's not synchronized with the clock, right? If we draw if we draw the reset like this, then it is asynchronous. However, if we want to have a synchronous reset, like this table here, for example, if we have the clock edge and my reset is 0, then my Q gets D. However, if we have a clock edge and my reset is 1, then my Q gets 0. So it's reset. Then we call this reset here, this reset, we call it a synchronous reset because it's synchronized with the clock edge. And we don't draw it this way, synchronous reset. We don't draw it this way. We draw it with the input D. Okay, we basically draw it with the input D. Okay, so who can tell me how we can implement this functionality here? So we have to control the D input here. So either. So we either have D or 0 depending on the input reset, right? So what do we have here? What do we have here? So we have two options, either 0 or D depending on reset. If reset is 1, we get 0. If reset is 0, we get D. What is this component here? What do we call it?
Multiplexer.
Multiplexer, excellent. Yes. So let me draw the multiplexer here. And it's a 2-to-1 multiplexer. This is 0, this is 1. And this is my select line, which is connected to reset. I want to, when reset is 1, I want to reset the flip-flop. Okay, when reset is 0, I want to load D. Okay, and let me, for simplicity, let me call this R instead of reset. Okay, so this is R. Okay, so this is a flip-flop, D flip-flop with synchronous reset input. Always when you have a synchronous reset input, it should affect the D input of the flip-flop. Okay, all right. Asynchronous inputs are drawn inside of the flip-flop, like inputs inside there. Okay, and of course I haven't shown you how to implement asynchronous reset, but you should be able to do it by manipulating the latches and the master slave flip-flop. You can manipulate it a little bit to implement the asynchronous reset. But this is the way to do that. And if you want, you can see that there is a 0 here, right? So my multiplexer may contract, right? May contract, isn't it? So what is the output here? Who can tell me what is the algebraic expression for the output? So when R is 0, I pick what? I pick D, right?
Yes.
And when R is 1, I pick what?
0.
0. And this is by algebraically, this is equal to R complement D. So it's nothing but an AND gate. This multiplexer is nothing but an AND gate. Okay, you can replace it with an AND gate in which I AND the reset complement with D. Notice that if reset is 1, then its complement will be 0, so the output will be 0, regardless of the value of D. Do you see that? Okay.
Yes, Doctor.
Yes.
What's the problem with the multiplexer?
No, I'm saying that you can optimize your design.
Okay.
Optimize your design. Usually, we try to avoid the what we call the redundant design. Okay, because the multiplexer has 2 AND gates. You can see here it has 2 AND gates and 1 OR gate and an inverter. Okay, we managed to reduce this to a single AND gate with an inverter. You see that?
Yes.
So this is designed by contraction, if you remember. Okay. All right. Now you understand the concept of synchronous reset. So now let us assume. So remember that our objective is to derive a method, okay, to divide our clock frequency by an arbitrary number. So we are going to do that eventually. Okay. Do you get the idea now? You get what we are trying to do? So we are going to use a modulo encounter for that. That has a reset input, but this is a synchronous reset. It's not asynchronous. Okay, synchronous reset. And we are drawing it inside here because this is a counter. It's not a flip-flop. Okay, so it has a reset, and we have to mention whether reset is synchronous or asynchronous for the counter. Okay. So we have a 4-bit up counter with synchronous reset and count enable input. What does count enable input mean? Means count if enable is 1 and stop counting if enable is 0. All right. Is this difficult to implement, guys? So if I go back to the synchronous counter now and tell you how do I implement the enable functionality here, the count enable functionality? Who can tell me, okay, how do I change this circuit such that I count if enable is 1 and I stop counting if enable is 0? Okay, I'm going to help you with that because we don't have time. Why did I do that? Because I'm going to need now to implement to load either Q0 or Q0 complement, depending on what? Depending on
enable.
On enable, excellent, yes. If enable is 0, I'm going to load Q0. And if enable is 1, I'm going to load Q0 complement. All right? Not only that, but I need to end this with enable as well, because also for the second bit, I don't want to toggle if enable is 0. I do not want to toggle. Additionally, I need it here as well, enable. See that? Okay. So this is an up counter with enable. Okay. So I'm going to erase my edits here.
Dr. White,
Yes.
I don't see why just adding enable in the Q0 will stop it from incrementing.
Okay. So let's say that enable is 0. Enable is 0. It means that all the multiplexers will select line number 0, isn't it?
Yes.
So line number 0. What is line number 0?
It is
Q0.
yes,
No change.
without the complement.
Here, no change. Here, no change. It will never change. If enable is 0, it will, the count will never change. Do you see that?
Yes. No, I understand. It's because when we complement it, we are actually increasing it.
Yes.
That's right.
It's yeah, okay, yeah. I mean, in a way, it's not exactly as what you said, but somehow, okay. So you can link toggling with incrementing, okay.
Yes, I
So
understand now. Thank you.
yeah, I'm going to remove the enable logic here, and then I'm going to assume that you understand it, okay. And going back to the counter now. Remember, I need to remind you again, okay, what we are trying to do. We are trying to, I'm sorry to do that many times, but I'm trying to, make sense of my exercises here, okay? So we are trying to divide the clock frequency by an arbitrary number. That is not a power of 2, okay? So for that, we use a modulo counter, and for the modulo counter, we have a synchronous reset input, okay, with a count enable. Okay, the count enable is not necessary for this exercise. For this reason, we are connecting it to 1. Okay, we're assuming that the count is always enabled for every clock cycle. Okay, so let us assume, for the sake of illustration, that we are ending Q1 with Q2 and then putting the result back in reset. Okay, so this is my reset signal, okay, synchronous reset signal that is fed back to the reset. So now my question to you, what is the frequency of this reset signal, or what is the period of this reset signal? If you know the period, you'll know the frequency, okay? So let's analyze this, and for the analysis, we first assume, without loss of generality here, okay, we assume that we start from all zeros. We start initially from all zeros, okay? And for this, if we start from all zeros, then the count sequence will be what? 0, okay, in binary, which is decimal 0, then 1, and 2, 3, 4, 5. All of these values, in all of these values, okay, for the state, okay, of the counter, this signal here is 0, okay, in all of these values. Why? Because Q2 ANDed with Q1 is 0, okay, you can see that Q2 ANDed with Q1 is 0 here, 0 here, 0 here, 0 here, 0 here, and 0 here. You see that? Then what happens? We reach 6 now. Once we reach 6, the signal becomes a 1, okay? Because the ANDing of these two becomes a 1. So the signal is 0 for all of these values, and then it becomes a 1, okay, for the 6th for the 7th clock cycle, okay? So we have here 6 clock cycles, okay, and then 1 clock cycle. And then what happens when this is the case? We basically apply a reset, a synchronous reset, okay, to our counter. So in the next clock cycle, we will go back to all zeros, okay? Do you get that? So after it becomes 6, okay, in the next clock cycle, it becomes all zeros, and then it repeats forever. So what is the period for our reset signal now? The period is 1, 2, 3, 4, 5, 6, 7. 7 times the period of the clock, original clock. Okay, so 7 times the period of the clock. All right, this is my period. So my frequency of this signal is the frequency of the clock divided by 7, right? So we managed to get frequency division by an arbitrary number, which is 7 now, okay? So how can we generalize this? We basically generalize this by changing the modulo counter, okay, to count up to some arbitrary other number, okay, other arbitrary number like 8 or 9 or whatever, okay. So in general, the synchronous reset signal of a modulo n counter, okay, has a frequency of f clock divided by n. Okay, f clock divided by n. Here we had a what? What is this counter, by the way? Modulo what? Modulo. What is this counter? Yes.
Modulo n counter n.
Yeah. What is n in
bit.
this case?
4 bits
7.
here.
What's that? 4-bit.
6.
Okay. So when you say modulo 6, what does it count to?
Modulo 6 counts up to 5, but this
Good.
one is modulo 7.
Excellent. So this is modulo 7, okay? And that's why the frequency of this signal here is this frequency here divided by 7, which is n, okay? So in general, if you have a modulo n, then the frequency of the reset signal, the synchronous reset signal is f clock divided by n. Clear? So what?
Yes,
okay. Okay. Let's have, for example, I would like to divide by divide by 11. We would like to divide the frequency by 11. Okay, how do we do that? Let me just go back to this circuit and then take whatever I don't need. I take out whatever I don't need. Just all right. Okay. So 11 is what? Is my n now. So n equals 11. So I need to count up to 10, right? So 10 in binary is 1010, right? So when this bit is 1 and this bit is 1, I should reset, right? Should reset in the next clock cycle. So I take Q1 and end it with Q3, and this is my reset signal. Okay, so this signal now, the frequency of reset is equal to frequency of clock divided by what? By 11, which is my n. Do you see that? Sometimes you have also parallel load for the counter. Okay, if you have parallel load functionality as well, then you can count from for example I to J. Okay, so you can for example if you reach the stop condition, like here, for example, let's say that you want to design a counter that counts from 5 to 10. Okay, 5 to 10. So when you reach 5, you don't reset. What do? You load what? You load 5. Okay, you load 5. All right. So a counter with parallel load functionality will have to have the inputs. Okay. All right. I hope this is clear.
Doctor, in this case, do we remove the reset?
You mean in the case of
From 5 to 10, for example?
Yeah, from 5 to 10, you don't need the reset. Actually, you don't need it. Maybe there, but you don't need it. Okay.
Yes. We connect the
You must have a parallel load functionality. So in this case, you may have for example, so counter counts from, for example, let's say 5 to 10. Okay, 10, right? So 5 is what in binary? 0 1 0 1. Okay, and 10 is 1 0 1 0. All right. Okay, so we have this counter here, which is a 4-bit up counter, right? And it has the inputs. All right, and I would like my some, maybe you have a reset input, okay, as well. Synchronous
can we, for
reset.
example, call it load because
And
it's
you
loading?
have to have a load. Yes, you have to have a load. Okay. In addition, for example, you can have reset and load both as the same counter. Okay. And you also have Q0 as output, Q1, Q2, and Q3. So the load is assumed to be synchronous here. Okay. Load is synchronous. Okay, with the clock. Synchronize the clock. So this is my clock, CLK, right? And I need to be able to load what? 1 0 1 0, which is 5 in binary, right? Yeah, but
Yes.
when do I load it? When I reach 10. In the next clock cycle, I need to load 5. Okay, so 10 is detected by ANDing these 2 bits. And I connect this to my load. So this will count. So we assume that, so there is a transient period. The transient period, okay, you never know what is going to happen, okay? So maybe you have what we call a preset input, okay? Preset input that will restart your counter, okay? So let's say that I have a preset input, so preset, okay, in which when it is 1, I will load the initial count. Okay, so this is my so if preset is 1, okay, or my I detect 10, okay, then I'm going to load 5 in the next clock cycle. Do you see that?
Yes.
So this is for initialization. But it could happen that if your preset is not there, okay, then and for example your counter is outside the count sequence, then you could have a transient period, okay, in which, for example, let's say that the counter starts from 14 or 13. Now in 13, this is 1 and this is 0. Okay, so it will count up to 14, right? In 14, this is 1, this is 1, so it will reset to 5. Do you see that? So this is a transient period that is ignored. Okay, it's not part of the steady state counting. Okay. Excellent. Okay. So this is a counter that counts from 5 to 10, and you could generalize this to whatever you want. Okay. Now, in addition to that, we can construct larger counters from smaller counters. Okay. Now, in order to do that, we have to have an output called carry out from our counter that will tell us that the counter will reset to the all zeros state in the next clock cycle. Okay. In addition to enable, when enable is 1, C out will be 1 if all the bits of the counter are 1. If all the bits of the counter are 1, then in the next clock cycle, they should be all zeros as well. Okay, so it's an overflow in a sense. Okay, it's an overflow. So it means that if you add 1 to all ones, okay, you'll have a carry out here. Okay, so you can think of it this way. But also you have to have your enable is 1. So this function here, this function, this output here is nothing but the ending of these bits here, Q3, Q2, Q1, Q0, ended with enable, because we must ensure that we are enabling the counting. Okay, so here we have a 4-bit counter with enable and with carry out functionality. Okay, that tells us whether we have reached the maximum potential of the counter or not, in addition to the enable is enabled. Okay, and it has an output of 4-bit here. Okay, and the clock, and we have another instance of the same counter. Okay, so that we implement an 8-bit up counter out of this out of these 2 4-bit up counters. Okay, so we connect my carry out to the enable of this counter. What does this mean? These are the most significant 4-bit, and these are the least significant 4 bits. Okay, so whenever this reaches the maximum potential and enable is 1, okay, we should enable the count of this counter, which means that this reached its maximum value, and we should count up once using this counter. Now we should increment this counter by 1. Okay, so if you are, for example, if you are counting up here, the first the least significant 4 bits are all ones, and my enable is 1 as well. Enable is 1, let's say. Then in the next clock cycle, these will go to 0, right? And you should add 1 to the next bit, right? Which is basically counting up using this counter. So the enable it means count up. Okay, means count up. Any question here? Did I lose you guys?
No, Doctor.
Are you with me? Okay, it will be great if you ask questions, because I'm sure that there is something not very clear. Otherwise, you'll ask. Okay, let's see. Who is this? Muhammad, is it Muhammad? Is your name Muhammad?
Yes, Doctor.
The person who said it's clear. I want the person who said it's clear. Who's that? Or Abdullah, is it? Okay, it's he's not responding. Okay, he's not responding. But I want somebody who says this is clear. I will ask him some questions about it. Can you explain? Yeah. Okay. You're back. You're Muhammad, right? You're the one who said it's clear, right?
I didn't say. I said we are with you, Doctor.
Okay. So you backed up a little bit now.
No,
so,
I will answer.
You'll answer, inshallah. Okay. So tell me what is the purpose of C out here?
C out is the enable for the next 4-bit counter. Okay,
C out equals 0. What does it mean?
C out equals 0. We never reach to 111. So the next counter will not be enabled.
Or enable is 0. Okay.
Okay. Yes.
Both. Okay. So if enable is 0 or the counter hasn't reached its maximum potential, then C out is 0. C out is 1. It means increment the next 4-bit by 1. Okay.
Yes.
So this is how you implement. Next, I'm going to discuss implementation of a 3-bit register, okay, that combines counting and register operations. Okay, let's do it quickly here. I have drawn it. I'm sorry about the way it's drawn. I'm going to clean it, inshallah, in the notes and try to make sure that it's. So this is my function table of my 3-bit register. Okay, it has two function selector bits. Okay, and 4 functionalities. Okay, if the function is 0, 0, then there is no change. If it is 0, 1, then it is a count up. If it is a 1, 0, then it's a count down. Okay, if it is 1, 1, then it is a parallel load. Okay, is this clear?
Yes.
Okay, now let's start with the easiest bit, which is bit number 0. Bit number 0, I have a 4-to-1 multiplexer. Okay, maybe I don't need that, but this is let's just start with this. Okay, and then you will see a refined version later. Okay, but for now, just understand that this design is not optimal. Okay, it's not optimal, but this is the simplest that you can get. Okay, so for 0, 0, if S1 S0 is 0, 0, then I shouldn't change the value of the bit. Okay, it's Q0. Okay, so here it's Q0, and here it's Q1 for Q1, and here it's Q2 for Q2. Okay, is this clear now? For 0, 1, okay, it's count up. Okay, and remember, for count up or count down, and for bit number 0, it's the same. We always complement every clock cycle. So we connect Q0 complement to line number 1 and line number 0, line number 2 of the multiplexer. Okay, so this will guarantee that when my function is 1, 0 or 0, 1, I will complement my Q0. Okay, because it's basically both of them are counting. When it is counting, the least significant bit is always complemented, regardless of whether we are counting up by 1 or counting down by 1. Okay, now for the next bit. Okay, next bit, what do we have? For count up, we have to find the condition at which we flip, and the condition at which we flip is different from counting up and counting down. So we use 2 multiplexers. For this, we use a 2-to-1 multiplexer, okay, in which Q0 will tell us whether we will flip or not. If Q0 is 1, then we flip. If Q0 is 0, then we don't flip. Okay? Here, Q0 complement will tell us whether we toggle or not. Okay? If Q0 complement is 1, then we toggle. If Q0 complement is 0, then we don't toggle. Okay, this is countdown. Okay, this is for countdown. And for the third bit, okay, it's the same. Okay, so we either toggle or don't toggle for both count up and count down. The only difference is in the condition at which we toggle. Okay, and for parallel load, we only have external inputs for each line here. Is this clear, guys? Any question?
Doctor,
Yes.
in the second circuit, you write D2 twice.
D2, where is that? This one. Oh, okay. Thank you. This is D1, not D2. I love it when someone corrects me. Okay, D1. Okay, means that they are paying attention. But the count up and down is clear to you, right? So can we for example, get rid of these two multiplexers and use only one multiplexer? Uh-huh. We need to know whether we are counting up or down, and how to do that. Basically by checking. For example, you can say, well, when S1 is 0, when S1 is 0, we are counting up, and when S1 is 1, we're counting down. And how do I recognize so basically, yeah. Or you can also take S0 is 1. When S0 is 1, we are counting up, and when S0 is 0, we are counting down. So then what do? You use one multiplexer. 0, this is 1, and this is QI, for example. Let's just make it simple and do it for Q1, for example. Okay, Q1 and Q1 complement. Okay, and this is going to be the selection line, going to be what? Let's take S0, S1 to identify our count direction. Okay, so if S1 is 0, then we count up. So we look for Q0 itself. If S1 is 1, okay, then we look for Q0 complement. Okay, so it's basically the XOR of S1 and Q0. And then this line here will work for both function 1 here, function 1 and 2, or data 1 and 2 for the multiplexer. So we saved on multiplexers here. Okay, also note that we can have a 3-to-1 multiplexer instead of 4-to-1 multiplexer. And a 3-to-1 multiplexer, for 3-to-1 multiplexer, okay, we can, what can we do? We can decompose it into 2-to-1 multiplexers, which is much better than a 4-to-1 multiplexer, okay, in terms of the number of gates. All right, so think, how can you minimize this circuit and optimize this circuit further? Okay, and I will do that, inshallah, in the notes, but think how to do it yourself. Okay, all right, any question? Is this clear, by the way? Is this clear? So we are using the same multiplexer for counting up and counting down here, okay? By simply, because when S1 is 0 and we are counting up, and when S1 is 1, we are counting down. Of course, you will not select this unless, you'll not select this line in the 4-to-1 multiplexer unless your S1 is 0 or 0, 1 or 1, 0. Okay, so in other cases, for example, 0, 0 or 1, 1, this will be a don't care. We don't care about this. Okay, all right, any question? Okay, let me stop here.